Let's make a start. So this one doesn't have a lecture in particular. This one specifically is going to be a review of chapters 2 to 7 of the Cambridge Unit 1 and 2. So basically what that means is I'm doing a full review of functions and relations. I think it's going to be like stuff like polynomials, transformations, range, domain, all those sort of fundamentals here. We're just going to go top to bottom, do a few questions. If I feel like they're a bit redundant, we'll move on. But otherwise, that's pretty much the agenda for this one. Doesn't make too much sense for breakout rooms for this. So I think what I'll do is if you do want to do the work ahead of time, I'll put in the chat specifically what we're doing. So if you want to grab a copy of your own books, you can follow along that way, that's fine. If you want to skip ahead, that's fine as well. But yeah, we'll give them a shot. So let's just start off with question 1. We have a polynomial, specifically a cubic polynomial with an additional unknown in it, unknown of a. It leaves a remainder of -4 when divided by x minus a. So again, we're using that a. And the goal is to figure out the possible values of a. So whenever the keyword remainder comes up in the context of polynomials, any thoughts on what might be relevant?
Remainder and factor theorem.
Remainder and factor theorem, correct, yeah. How do we use remainder theorem usually?
I forgot.
That's fine, yeah. Anyone else remember remainder or factor theorem? What that equation is? All good. So remainder theorem, f of -b over a is equal to the remainder, whatever the remainder is. Now, worth pointing out, f of x is the function that we care about. So in this case, we should technically be saying p here instead of f because we've got to use that polynomial. Now, as for what the b and the a come from, they come from the generic linear ax minus b. Oh, sorry, ax plus b. My bad. Ax plus b. And that's where you take those from. Now, in our case, we specifically have x minus a. So in our circumstances, we have this a is equal to 1, and we have this b is equal to negative a. So essentially what we have is p of, so that's going to be a 1, negative a makes it positive a, and therefore this is going to be equal to our remainder, which we're told is -4. All right, so we can put in -4 there. And so effectively all we're doing from here is solving a, where p of a is equal to -4. So we'll pop everything in there. So if we rewrite out what the full p of x is, we now have 6a cubed, 6a cubed plus 5a squared, 5a squared minus 12a, and then that equals -4. We have to solve this. So, what methods do we remember when it comes to solving polynomials?
Chris, is there one where we can look at the constant in the equation and then do trial and error?
Yeah, there's a trial and error. Absolutely there is. Yeah, so it is still using, again, remainder theorem, but more specifically factor theorem, technically speaking. And so all we're going to do is rewrite this to make the polynomial equal 0. So we'll make this as a +4 equals 0. And what you're talking about is essentially looking at factors of this and then plugging it, the plus or minus versions of those, into the polynomial to eventually get 0, is what we're targeting. There's a bit more of a nuance to that though, and it's got to do with this. When you have a coefficient here, how do we have to modify that approach?
Do we factor it out of the polynomial?
If you can. If you can cleanly factor it all the way out, then that would make life a lot easier. Divide everything by 6. Although that will give us fractions to work with here, which is a little bit less pleasant. So we're kind of stuck with it for a little bit. Basically, what it means is we're going to try both of these factors. So these are going to be alpha factors. These are going to be beta factors. And essentially what we're testing is, once again, f of negative b over a, but in this case it's like beta over alpha. But we're doing it with these particular factors. So if we think about alpha factors, we're looking at 6 and 1, the plus minuses of both. And we're looking at plus minus 2, plus minus 3. Those are the possibilities there. And then for this, we got plus minus 1, plus minus 4, plus minus 2. Those combinations. So obviously that's a lot of combinations. In the case of Tech3, they'll try to make life easier, where in the case of, this is specifically called rational root theorem, when you have these additional factors, when you do have them, usually what they do is they don't put this as the answer, but they do use these as your denominators. And so you just pick the easiest from there, which would be having numerator 1, denominator 2, or the negative equivalent of that. And so yeah, like for instance, one of the possibilities could be we're doing p of a half, right? Take the positive 1 and the positive 2. You do this factor divided by this factor. Now, that's going to be a lot of handwriting. I'm sure we all know how to sub things in and solve. If you're not too familiar with simplifying those, it's really just a practice thing. I can't exactly show you better ways of doing that. And so what we're just going to do is we're going to just practice a few, or just bash out a few on the CAS. So let's define our function. I'll just use typical old h of x, and we'll bring it back. No, it's fine. We'll do p. Let's make it really specific. P of a is 6a cubed plus 5a squared minus 12a plus 4. And then we do our tests. So one of the possible tests that I had written down there was doing a half. And luckily enough, that actually does come out to be 0 there. So we've hit what we wanted to hit. That does in fact equal 0. What do we do now that we know that equals 0? Remember, we're basically just doing factor theorem again. These terms help us with what? They help us with the linear. So basically, when you do factor theorem, what you're essentially doing is finding the coefficients of some linear that would be a factor of your polynomial. It helps you find, in this case I'm writing as alpha x plus beta, just to be specific with what we've written notation-wise, but it is the same thing, ax plus b. I'm just trying to be separating the questions. And so if f of negative beta over alpha equals 0, using our factor theorem, then that means that we now have negative beta is equal to 1, because we just compare numerators, in which case you've got beta equals negative 1, and you've got alpha equals 2, just because you compare denominators as well. And so basically what we've identified is that 2x minus 1 is a factor of our polynomial. So that helps us in some way. Why does it, oh sorry, I guess I should write little a, because our polynomial is a. So 2a minus 1 is a factor of this a polynomial. How does that help us actually solve it? It does, but how does it help us solve it? we think of factor, what other terms come to mind? Or what kinds of concepts come to mind when we think of factors? Factorizing. How do we use 2a minus 1 being a factor to help factorize a polynomial? Polynomial division. We use polynomial division. I know this is probably a lot of refreshing, but this is an old topic. But basically, you take whatever the factor is, you put the entire polynomial underneath. So in this case, we got the, in fact, I'll copy it from the CAS, so I don't have to keep scrolling back and forth. We do 6a cubed plus 5a squared minus 12a plus 4. And then we essentially do a polynomial division, because what that'll essentially do is convert this cubic into a quadratic up here, and from there you'll have linear times quadratic equals 0, and you can use null factor law to solve it. So that's why it's a good idea. Does anyone remember how we do polynomial division?
Chris, do we divide by the leading term?
Yeah, leading terms, absolutely. Got this one and this one. So the one in the middle is the numerator, one in the bottom, or the left is the denominator. So you got 6a cubed divided by 2a, looking at 3a squared. Now that we have that, what do we do with that 3a squared?
Does it have something to do with multiplying with the second term?
Exactly what it does, yeah. You multiply through both of those terms, and then you put it down on the bottom. So basically you have 3a squared multiplied by 2a will always get you back to where you started, but then you got 3a squared multiplied by -1, so minus 3a squared. That's it. There's one final step to complete the full iteration of one go through. What's the last little thing we got to do before we repeat the process?
Subtract.
Subtract is correct, yeah. Now, pro tip, maybe pro tip, I don't know. My tip is you put brackets around it, because if you don't, I found that sometimes students will think you just put a minus on this and then just leave this as whatever. You do want to minus everything. So for instance, 6a cubed minus 6a cubed, 0. 5a squared minus 3a squared. So they cancel down to a plus. So 5, 6, 7, 8 a squared. Then you can drop everything else down. Sometimes the answers get lazy and they don't bother dropping it down. I think it's nice to have the whole thing in one state, so you can always just look in one spot and then repeat the process from here. Which is exactly what we do, repeat the process from here. You take this one, divide it by that, just like how we took this one and divided it by that. So we're looking at 4a. 4a goes back in to make 8a squared, and then minus 4a, because you're once again multiplying all the way through. Do a subtraction. It's going to cancel this one down always, and then minus 12 minus 4, so we're looking at 8. Oh, sorry, minus 8. And then, because you know it's already going to be a factor, you don't really have to finish this one all the way out. You can just chuck this up, so minus 8a divided by 2a, you're looking at minus 4. If you do bring the minus 4 all the way back in, you will find that it will all cancel down to 0. And that can just be at least maybe a nice way of knowing that you've done the polynomial division correctly when you do your subtraction. Oh, sorry, hang on. Now I should double check it. Minus 4 times minus 1 would have made this a plus, not a minus. So there you go. Oh, I stuffed up right at the end where it didn't matter. But yeah, point being is if you get 0 at the end, at least then you'll know you've done the polynomial division right. But technically speaking, if you've done it correctly, you don't have to waste time doing these last few calculations. You just need that minus 4 at the end and then you're sorted. But okay, so now that we have this at the top, does anyone know what we do with it? All good. So reminder that our whole goal is solve this. That's what we're trying to do. And so when we solve polynomials, the way to solve it is through factorization. And so what we've done here is essentially doing our best to try and factorize it. We know 2a minus 1 is a factor. When you divide something by a factor, what you get is another factor. So both of these two things are factors of that cubic. And so what essentially we've achieved is we can say what we had was 2a minus 1 multiplied by the quadratic that we have there. So we had 3a squared plus 4a minus 4. That is the same thing as this whole thing. We've taken a cubic that's separated by a bunch of pluses and minuses, and we've now rewritten it as a product of two terms. That's the advantage of doing the polynomial division method, because now you have null factor law here. So either this one equals 0 or this one equals 0. This one's super chill. That's just going to be 2a minus 1 equals 0, a equals a half. Quadratic, a bit tougher. 3a squared plus 4a minus 4 equals 0. How do we solve this? Or what's like, we got a couple of methods. How might we solve that quadratic?
Chris, you can like there's like this technique that I know from school, right? You can multiply the first and the third term together.
Yeah, so 3 and negative 4, or do
Yeah.
you do 3a squared and negative
No,
4?
like the 3 and -4.
Yep,
And then you get -12, right? And
yep,
then you want to find two numbers that like multiply to -12 but add to like +4.
yep,
And that's 6 and -2.
yep.
And then like because 3 and 6 are like they're multiples, and so you want to like rewrite the +4a as 3a squared plus 6a minus 2a minus 4.
Wait, hang on. What, write that one again, sorry.
So now you can write like the quadratic as 3a squared
Yep,
plus 6a
yep.
minus 2a
hmm
and minus 4 is equal to 0.
Oh,
And
so you're splitting this up into the 6 and negative 2.
yeah,
Yep.
and then you can just factorize like um the first two terms becomes
Ah,
3a
you did grouping.
3a times a plus 2, and then the other one
3a,
becomes
oh
like
yeah.
you take out the -2 and you also have a plus 2 inside.
Yeah,
And then by grouping, I think the factors are a plus 2 and 3a minus 2.
exactly right, yeah. A plus 2, 3a minus 2. Yeah, that's kind of cool. So, yeah, basically to say that back, you take these two terms. It's like doing the add together times together method for when there's no coefficient here, but the things that you're doing the times together by is the a and the c. So you do your 3 by -4 gives you -12. You figure out what split, what two numbers give you multiple to give -12. That's this. You split this one up into both of those coefficients, and then grouping from there. That's cool. I like it. Reminder that, of course, this whole thing was equaling 0 to begin with, and so we're going to put an equal 0 there. And now this is nothing, right? Like now it's just a equals 2, a equals 213. And so final answer, you got a half, 2, and 213. You just put them all in one little statement at the end. Nice, I like it. Big question to start with, geez. Yeah, right off the bat, big polynomial division, factorizing, and then quadratic. No, still helpful for sure. I know this sort of stuff does appear on SACs at the very least. They don't usually waste too much time on this with exams, but definitely in SACs. Okay, that's that one. Question 2. Express quadratic in another quadratic form. So I'll write it down. I don't know if we'll do too much of the actual arithmetic of it. Can anyone tell me what's going on in question 2a?
Chris, I think it's asking us to complete the square.
It is asking us to complete the square, absolutely. Yeah, completing the square, I think this is probably pretty chill for most people. If anyone wants to see me complete the square, then let me know. We can do a bit of revision on that. But otherwise, yes, we are just completing the square. So I'll just sort of cheat that out real quick. 25. Oh yeah, here we go. Actually, this could be nice to know. How to actually complete the square. Only doable on TI Inspire, by the way. For whatever reason, Casio doesn't have a complete square function. I've looked for it. If anyone knows where it is, let me know, but I'm pretty sure it doesn't exist. Anyway, Cas has one, or TI Inspire rather, has one. X squared plus 8x plus 9, comma x, bang. Reason why I'm doing it is because it's going to help us with the second question, part B, for which value is that quadratic A minimum. And the fact that this is x plus 4 all squared minus 7 is going to be helpful for that. For what value of x do we achieve a minimum? Reminder, when you complete the square, nothing really, like the functions are still identical. So saying the top one, where's the minimum of the top one, is the same thing as saying where's the minimum of the bottom one. Bottom one's a lot easier to use. Why? Okay. When we say we want to find a minimum of something, in the context of graphing, what does that mean?
Would it be the turning point?
Yeah, it's going to be the turning point in this case specifically. But broadly speaking, we're talking about the smallest possible y value on the function. That's what a minimum is. And in the context of quadratics, absolutely, it's going to be the turning point because this is a positive quadratic. So if we're looking to figure out what the x value is that gives us a minimum, what's that going to end up being in this case?
Would it be -7 when the x, because it's a positive 4, would be -4?
Yeah, correct. So you're given both answers there. You're given what the actual minimum is, -7, and the x value that gives you the minimum, which would be -4, because as you've seen, yeah, +4 means shift left by 4. It's good. Nice. Thank you. Okay, next up. Similar kind of question. We've got a linear, find the range. This is probably going to be pretty chill. Let's see how we go. I'll write it out. If someone knows what we're doing before I finish it, that's fine as well. Minus x. And you want to find the range of 6 minus x. How do we find the range of a function? What is the range of a function?
The lowest to the highest y.
Yeah, exactly right. So how are we going to, now that we know we're looking for lowest to highest y value, how do we actually find what those are?
Could you just substitute the x in?
Yeah, just subbing the x's in is correct. The linear is what's referred to as an increasing, or technically strictly increasing graph. That or decreasing, rather, because we've got a negative here. It's going downwards as we go from left to right. And so basically what that means is, if you know you're strictly increasing or decreasing, then the range is always going to be found, or can always be found, by just looking at where the endpoints end up being. And then we chop it off from there. Now, word of warning, if you have a quadratic and it's defined from here to here, if you sub in the endpoints, you get it wrong. And the reason why is because you've missed this turning point. This is not a strictly increasing or decreasing graph. And so whether you sub in the endpoints will depend on what type of graph you have. But yes, works out perfectly fine in this case. Drawing a quick graph can maybe help out with that a little bit to figure out, it'll always help, but it'll depend on how fast you're able to draw a quick sketch of the thing based on if it's going to be worth it or not. But yeah, just keep in mind what functions you have and if you can just go end to end or not. But yeah, this one's pretty chill. Sub in x equals 5, sum in x equals -3. That's going to give you this and this respectively, and that's going to be your range. Easy. Okay, transformations. We've done a lot on transformations. I think we'll at least do... Well, actually, no, the dots are the same. Question. Alright, fair enough. The weird part is that we're doing the graph of y squared equals x. I'm just going to change that to y equals root x, just because we typically don't do y squared equals x as a function. We want to dilate factor 2 from the x, and then translate 3 in the negative y. So I don't really care what method you use to solve this. I'm happy if you want to do point form, I'm happy if you want to do by recognition with the function notation. I'll be even happier when this starts to zoom in. There we go. Cool. The first things first. We got dilate of 2 from x, and we've got translate 3 negative y, so -3 in the y. What are we going to do?
Could you map it?
Yep. So when you say the mapping, you're talking like x dash y dash stuff?
Yeah.
Yep, certainly. So the mapping approach would mean starting at x, y, and then, well, what's the next one if we do our dilate of 2 from x? What do we get?
2 x. No, 2 y.
2y is correct, yeah. So the keyword from means you do the opposite variable. If it said along, then you would keep the same variable. But yeah, that's good. Good catch. And then translate -3 in the y direction. What's that?
Just be x, take away 3.
X -3?
But if it's in a bracket, it would be positive because it's going in the other direction.
The other direction.
So it'll be positive.
Okay, so this is the challenge between doing the mapping version versus doing the by recognition version. Because when we think about translations, or specifically horizontal translations, we always think of them as opposites. So like minus is right and plus is left. When it's mapping specifically, you go back to what's intuitive. So if we say -3 in the y direction, we literally mean subtract 3 on the y.
Oh, it's because when you rearrange it, it becomes -3 anyway.
That's correct. Yeah, it's when the rearranging happens where you observe that flip. Now, technically speaking, because it's the y, it's not going to happen. It's going to flip and then flip again. But if it was a horizontal translation, then yes, it would stay flipped. But yeah, that's going to give us our x dash equals x, y dash equals 2y minus 3. What do we do once we have that? Remember, the goal is to somehow put these transformations in here. Something we've got to do right before putting those in there. I don't know if the mic picked up what you said. I saw you unmuted. Or maybe you were just thinking. One step right before it, and that's to rearrange for x and y first. Because x dash and y dash aren't variables in this function. X and y are. And so if we want to substitute to actually figure out what's going on, then, well, we're going to have to do a bit of rearranging. Now I'm hoping this will, yeah, it is focusing. Cool. So, I mean, you can just flip those around if you like, but more importantly is rearranging this other side to get in terms of y and x. But okay, now that we have it rearranged, what can we do with these?
We just square the whole thing.
Square the whole thing? Not quite in this case. No, we don't want to do any rearranging over here.
Chris, can we apply the translations to the root x?
By the translations to the root x. How do you mean?
Like, okay, so you've got it in the transformation thing. Like, hold on. Oh, are we trying to graph this?
Not graph it. No, we're trying to figure out what this function looks like after these are applied.
Okay, hold on.
Mhm.
So obviously it's gonna translate downwards,
Yeah, it'll go downwards.
and dilation of factor 2 from the x-axis. Does that mean it becomes like sort of like less sharp of a turn?
Less
The root
sharp.
function?
Let's think. Less sharp. It'll stretch. It'll multiply by 2 all the y values. So essentially, instead of doing
Yeah, so
this,
it stretches like upwards basically.
yeah, it'll do that. Yeah. So the sharpness of the turn technically maintains exactly as steep it was. Wait, does it? No. I guess it depends on how you define the steepness of the turn. Yeah, anyway, point being is it does this. Yeah. That's what it does, but as far as like getting the actual equation going on, what do we do? We're one step away from getting our actual equation that describes it all. Yes, you are right, it stretches it by 2 and it shifts it down by 3. How do you actually write the rule that describes that?
Could you just substitute that equation into this where y equals the root x?
That's exactly it. You've got y equals this thing, so you can replace this y with this thing. Yeah. Now at this point we do knock off the y dashes because it's a new function now, and yeah, it's just sort of practice is what it does. You just knock off the dashes, and since x is x dash, we don't really change anything there. All you would do from here is rearrange. Oops, that's not how you do that. 2 root x minus 3. So this is probably a bit more of a heavyweight way of going about it. If you have a whole bunch of transformations, this is really helpful to have everything ahead of time to know what's going on. And technically speaking, this is, you had dilations, you had translations, made it a bit tough. The other approach to this is by recognition, which means you have to know, like, where does a dilate of 2 go? So you start with your root x, dilate 2 from the x means you put it there. Then from there, translate of 3 down in the y. You have to then start from here and then do a translate. Now there's things to consider when it gets more complicated, but yeah, it's fine to do either way. Both works. Cool. All right, that's that. Question 5 is also transformations. I think we can skip that. 6 is a... If someone can tell me how to do 6a, I won't necessarily do the arithmetic for it. It's a pretty common thing. You have linear divided by linear, and you want to make it look like a hyperbola. There's a couple of ways you can do it, but there's one that works every single time, and there's one that works where you have to do a bit of intuition that differs from thing to thing.
Chris, can you multiply by x plus 1 over x plus 1? Or I'm not sure because it's equal to 1.
Yeah, you can. Here's what that's going to look like, though.
Oh, it's going to become quadratic on the bottom.
Yeah, it's going to go bigger. That's fine. It's a decent idea. You're thinking about like the algebra of how you might split things up. That's fine. Algebra. See, thinking about the algebra, this is what I was saying, which was like it's going to differ from what numbers you have every single time. It's going to be a slightly different approach. Definitely works, but a little bit different. There's one surefire way that makes it work. And we've actually done the technique today. We've done the technique today that can work for this one. So that'll really narrow it down. We've only done a few things. Someone's got to know it. Nah, that's fine. So it's polynomial division. Whenever you have, because linear is technically a polynomial, it's a first order polynomial or first degree polynomial, and it's being divided by another linear. All right, and so whenever you have polynomial divided by linear, you have a polynomial division there. And so essentially what goes on is you take the denominator of your thing, which is x plus 1, and you divide the numerator, which is 4x minus 7. Now this is a very quick polynomial division. You're just going to have 4 on top, minus 4x, and then the 4, 0, minus 7, minus 4, so 7, 8, 9, 10, 11, minus 11. And so this is a different kind of polynomial division where you have a remainder. And so basically the way it works is you have your fraction that you started with, the 4x minus 7 over x plus 1, and that is the same thing as the quotient, which is the whole, like the perfectly divisible portion of it, plus the remainder, which happens to be negative. And all of a sudden you've got a hyperbola. All I have to do is flip the order of those terms. Negative 11 on x plus 1 plus 4. And all of a sudden we've got our a and b. A is negative 11 and b is 4. So polynomial division will always work. And it's a pretty quick thing too, right? Like you do it pretty fast. But if for whatever reason you're really strong at algebra and you want to do an algebra approach, yeah, okay, why not? I'll talk about it just in case you're interested in it. I don't necessarily recommend it though. Point being is you want to try and rewrite this function in a way where you have x plus 1 on the numerator. And one of the ways you can do that, I'm just going to kind of do it, is you have 4x plus 4. And because I've introduced a plus 4, I need to have a minus 4 associated with this. So 7, so that's minus 11, right? I've introduced a plus 4, and therefore I've got to take it away as well. Now, the reason why I've done that is because I've got 4 as a common factor in both the the 4x and the 4, so I can take that out the front, right? So I can have 4 bracket x plus 1, and then minus 11 over x plus 1. All I do from there is split the fraction. So I have this as its own set of fraction, and this as its own set. So that's going to give me the minus 11 on x plus 1 that we had earlier. But then if you notice, when looking at specifically this side of things, x plus 1's cancel, leaving you with just the 4. And so that also gets you there, but you got to think a bit harder about how you might do it. Up to you. Both of those methods work. I guess it all just depends on how strong you can foresee algebra. But okay, that's that one. Next up from there, find coordinates of intersection with the axes. Okay, so we have our function. That's this one here. Find the coordinates of the points of intersection. Geez, that's a really weird way of wording that. Coordinates of the points of intersection of the graph with the axes. In plain English, does anyone know what that's actually asking us to do? Someone can do a better job of writing this question than the question writer. What are we being asked to do there?
We're trying to find the x and y intercepts.
There we go. Look at that in real English, as opposed to whatever this was. Yeah, points of intersection with the axes are in fact the x and y intercepts. How do we find x and y intercepts? Same method every function.
So
We make either y or x 0, depending on which variable we're trying to find.
Yeah, the opposite. So if you want to do x-intercept y equals 0, if you want to do y-intercept x equals 0. That's just a bit of algebra. I'm sure you guys are fine with doing what's effectively linear algebra. What's maybe a bit more different are the equations of the asymptotes. So if we zoom right in on that hyperbola, how do we know where the asymptotes are?
We can look at the translations.
We can't look at the translations, yeah?
So the horizontal asymptote would be at y is equal to 4, I think.
Yes, yep.
And the vertical asymptote will be at x is equal to -1.
That's it, yeah. Sort of like put a graph on that. The wording around that feels weird because when you think vertical translation, you'd think vertical asymptote, but in fact, there's your y equals 4, and there's your x equals -1. So yeah, it is just using those translations, and then of course you fill in the rest of the hyperbola based on based on if it's positive or negative. But that is not the question, so we can move on. Okay, which means points, vertices of a triangle. M and N are midpoints. Find. Okay, so just find midpoint. Cool. We're not going to do all of them. We'll at least do M, and then if I need it, we'll copy down N. So M, we're told, is the midpoint of AB. So if we have A bracket -2, 1, and we have B bracket 3, -4, how do we find the midpoint between them?
you just add them together divided by 2.
Yeah, precisely. Add together, divide by 2. -2 plus 3 divided by 2. 1 plus -4 divided by 2. Midpoint is therefore 1/2, -3 on 2. Awesome. Okay, the second part of that is to prove that MN is parallel to BC. So we may or may not do the actual arithmetic on it. I'll just kind of draw some random points. Basically, we're going to have like point here, point here, point here, point here, and we're trying to prove that these are parallel to each other. Let's fix that. So when we think about parallel, or proving things are parallel, what's the first thing that comes to mind?
Would it be the gradient?
Gradient, yeah. Gradient's got definitely something to do with it. What's specifically about gradient?
Well, they must be the same.
Must be the same.
The translation can be different.
Yes, translation can be different. In fact, I think it has to be different. I don't know if you can have overlapping lines be considered parallel. But that's just a nuance, whatever. Point being, yes, you want to have gradient same. How do we prove that these are the same gradient? So let's just say we know the points that are there. If all you knew were the points, how could you prove these gradients are the same? Point gradient method. Gradient point. Yeah. So gradient point formula gets you y equals mx plus c, which is fine. It goes further than you need it, but it definitely works. Because you don't necessarily need y equals mx plus c. You need... I mean, I might just be misinterpreting what you mean by point gradient method. But basically, yeah, you calculate gradient of this one by doing your rise over run. So your y2 take y1 and x2 take x1. Exact same thing over here, and those are going to be the same value, essentially. The way I think about point gradient method is like when you find the full y equals mx plus c, which is still fine, right? You'll get two different y equals mx plus c's, but then you'll just compare these m's together, and you'll say, good to go. But yeah, that's good. Awesome. All right, let's cross that out. That's that. There's more remainder theorem stuff. I think we can skip that. That takes forever. That's just subbing in some stuff. I think that's going to be fine. I think some of these are going to be fine. Inequality is going to be fine. Oh yeah, simultaneous might be good. It's a fun one too. So question 11. There's a simultaneous going on in there. I'll spend some time copying it down. In the meantime, someone can think about how we might go about solving it. This one doesn't seem to leave a lot of flexibility in how it's solved. There's certainly one method that's coming to mind that's very dominant. Ignoring the complexity of the question then, there's only really two methods we use for solving simultaneous. What methods are they?
Substitution and elimination.
That's it. Yeah, so you've got two choices now. That really narrows down exactly what we should be doing. Which one seems more appropriate for this scenario?
Well, I just usually use substitution because it's easier.
Yeah, totally. And in most cases, it's pretty much the only thing you need, because elimination really only sort of shines bright when you have like maybe 3 or more variables that you're working with, because it has the opportunity of cancelling out more than one at a time. So yeah, substitution saves, like it always works. It's good. There's definitely one easy way of going about this and one hard way of going about this. How would we start this one off if we're talking substitution?
Just for the top one, you could make like y or x take away 5.
Yeah, totally.
Oh.
So let's say we have y equals 5 minus x. That's our new equation 1. Cool. And then what are we going to do with that?
Sub it into the second.
Yeah, take all of this, chuck it in there. You know, you'll expand out the quadratics. You'll just have another quadratic to solve. I think we've already covered enough how to solve quadratics. So you'll get a couple of possibilities for x there. So let's just say we got two answers: x1 equals 3, x2 equals 4. Because quadratics are likely to have two solutions. What would you do now that you have your two possible x values? So like we've done all of our working to sub in equation 1 into equation 2, and this is the net result of it. We need to solve both x and y. How can we get y?
Don't you sub it back into the other equation to find the other variable?
Yeah. Now technically you can sub into either equation 1 or equation 2. One of those is significantly easier. So putting it into equation 1, much easier. And it's going to give you two possible y values. y1 and y2, whatever those are. Under some circumstances, there might be domains associated with x and y. And so for that reason, you might be able to cross off one or more of these answers. Hopefully not more. Granted also, not all quadratics do have two solutions. It might have been the case this one only had one. It might have even been the case this one had 0, although that's pretty rare for it to have 0. If it does have 0, you just say no solution to simultaneous, and then that's pretty much it. Yeah. Easy. Show that points form a rhombus. Yeah, whatever. That's a pretty weird question. Turning point form we've already seen. Intersection. I mean, we'll briefly talk about it. Question 14. Finding the coordinates of intersection between graphs. I know I've definitely got a couple of students here and there that always tend to forget how to find intersection between graphs. Maybe someone here remembers. How do we find the intersection between graphs?
Is this another substitution thing?
Correct. Yeah, no, that's exactly it. Another substitution. You've got y equals this, you've got y equals this, therefore they must both be equal to each other. So for instance, in the context of 14a, you would have 4x plus 1 equals x squared plus 3x minus 9. And then you go from there, simultaneous essentially. Yeah, like all coordinates of intersection are basically simultaneous equations, what we just did. Inequalities in the context of polynomials is a little bit different to how you solve linear inequalities, so I think it's worth touching on. I'll do a slightly easier example just so we can talk about it quicker. So if I copy down, for instance, part C, we have x minus 3 all squared, bracket x plus 4 greater than equal to 0. The fact that I chose a factorized question rather than an expanded one should at least give maybe a tiny hint how we might do this a bit easier. How do I know whether this is greater than or equal to 0? There's actually a few ways you can do it. Tough, isn't it? There's a couple of ways you can do it. There's one where you do what's referred to as sign analysis, which basically means this statement here just says, where is this thing positive? Or 0 technically, but where is this thing positive? And so the only way something can be positive is if this times this gives you a positive, which means you either have both of these be positive or both of them being negative. If you multiply the negative by negative, you get positive. Positive by positive, you also get positive. That's a lot of work because you've got to figure out where is this thing positive, where is it negative, where is this thing positive, where is it negative. Better off is sketching the whole polynomial first. So does anyone remember how to sketch polynomials like this? You have a squared term, you have a linear term. Anyone remember what those tell us about the graph? Turning points. So the squared one specifically tells us where the turning point's going to be, and the linear will tell us that it's a cut through the x-axis. Cool. So x minus 3 means we're going to have a turning point at 3, because it's the squared one. And then x plus 4 means we're going to have a cut at minus 4. Cool. Now the other thing to consider here is overall shape, right? This is a... What type of graph is this? It's a type of polynomial. What degree polynomial is it?
Would it be a third?
Yeah, third degree polynomial. It's cubic. So what do we know about how a cubic is going to look if I were to draw a curve? Because there's a couple ways I could do this. Only one of them is correct. One would be to cut like this and turn like that. The other would be to cut like this and turn like that. So I've got two possibilities based on what we've discussed so far. Only one of them's correct. How would we know?
Would it be the positive?
Yes,
So it's
exactly.
going up.
That's good. Yeah, it's a positive cubic. So if you think about like the very basic cubic, positive cubic, start bottom left, end top right. And so for that reason, we'll do exactly that. We'll start at the bottom left, cut where we're told to cut, turn wherever it feels convenient, and then turn where we need to. This turning point over here, you won't be able to solve that until you learn calculus. And even when you do learn calculus, you'll look at this and you realize, I don't want to diff this. This feels awful. And so, realistically speaking, where you draw this turning point, in Unit 1 and 2, they don't actually care. All right, as long as you draw the right-ish shape, like you might have it bend a little bit further out here than otherwise. As long as you're getting starts bottom left, ends top right, turns here, cuts here. And I mean, you can also like solve your y-intercept as well, but point being is you don't actually really need that for this one. That's for graphing. Now, why did graphing matter? Well, this just means where is my function, positive or 0? Specifically over what x domain is it positive or 0? Well, now that we're looking at it, where is my graph positive or 0?
When it's greater than -4.
Yeah. Specifically greater than or equal to -4, because we do want to include that 0, but otherwise, yeah, that's still perfectly fine. Nice. So when we give our answer, if you want to give it in a fancy way, you say x is an element of -4 to infinity. You could say x greater than or equal to -4. That's about it. You can get fancier and more stupid, ridiculous ways of writing it, but that's like, why bother? Yeah, that's pretty much it. So we did a decent review here. We did a decent amount of polynomial stuff. So refresher on sketching polynomials, some simultaneous, a bit of linear, poly division, a bit of transformations, complete square, factorizing. Yeah, okay. Cool. All right. I mean, it sounds like it was due, considering there was a lot of hints to be given, but that's fine. That's what you're here for, to relearn things that haven't been looked at for a while. Easy. All right. If there's anything to clarify further, please let me know. Otherwise, I'll leave you to enjoy the rest of your day. Take care.